Hello, everyone. This is Kirsch and Chilli Dan here with another design review. Uh, this board has been submitted by John Vedder. It's a very interesting design, pretty straightforward, power supply that takes in 24 volts and outputs it to produce 15 volts and negative 15 volts. It's got some capacitors and whatnot. We're going to dive into the schematic and then into the PCB layout. And of course, you know, we're always going to talk about the fields and other practical things when it comes to PCB design and layout. Welcome, and we'll start with the design. Hello, Dan.
Hi, good day, everyone. Welcome to the Kirsch and Chilli Dan show. We appreciate your attendance and pay attention to our focus on what we hope will be a helpful perspective on the design. This one, like Kirsch was saying, is a fairly straightforward. I just want to comment that it's a nicely drawn schematic. It's very easy to understand. The flow left to right makes it something that I can quickly review. The only thing I had commented about was that on the output circuit, both of these have a 1 microfarad and a 100 microfarad capacitor. And unless the manufacturer has determined that you need that small value capacitor for stability, when you look in the scheme of things, 100 plus 1 is 101. So the 1 microfarad cap is not doing a whole lot of heavy lifting. If you did want to improve the energy flow into and out of that part of the circuit, I would replace the 100 mic with 247s, because then you have half the ESR, half the source impedance, and more energy per wave cycle. But other than that, this is quite a functional schematic from what we see today.
Awesome. And yeah, it looks great to me as well. What I would add on here is some title text. You know, it does have that. And then also I would put like, this is supposed to be getting power in from a transformer. So I would probably drop an image of a transformer on the left side so that the reviewers or whoever's looking at it can immediately know transformers coming in and an output.
All right. And that it's a 24 volt AC transformer is what the intent is here. So yes. And then it says V positive and V negative. I would certainly want to note that this was plus 15 and minus 15 volts.
Mm-hmm. All right. We'll head over to the PCB layout, and we're going to look at the top layer now. Here you go.
Okay. So the first thing jumps out is that there's not a lot of copper left on the top layer. I hate wasting material. I don't think you can buy a core of PCB material that has only these few spots left on it. So the first thing they've done is to remove all of that copper on layer 1. And there are a lot of things that happen there. Then you've basically consumed a bunch of acid and created more waste, which is something that everybody wants to try to avoid. And the other thing is that you have taken away your chances for using 2 different copper layers to create transmission lines between the layers. So from left to right, there's no copper here. So we know that we're going to have very, very high impedance transmission lines as a result of that design philosophy. So the first thing I would suggest is that we would review the reasons for trying to take all this copper off. Okay, that's layer 1. And then the other thing, I think we did note that in the design that there are reference designations there. In my symbol libraries, what I try to do is where the little boxes that show component placement are, is you put a little tail on the pin 1 side just to make debugging easier. Then you don't have to think about where is pin 1, and the same thing, whether it be these 3 transistors or the 2 transistors that you would mark pin 1. Now, in the footprint, you can see the square pin on the 3-pin transistor, and that's typically means that that's pin 1. And I see that also in several of the other footprints, that there's a square and a round one. That certainly does fulfill part of the need, but there are a number of other components that do not have the square. So the convention that I like to see is just to take that little box that you're already silk screening and add a tail on the pin one side. And that makes it very straightforward, quick to see, and easy for you to debug your circuit board. So a note for anybody that's out there doing this type of design.
All right, I'll pull up the second layer of copper.
So this is good because we see a nice flow from left to right. The energy is going to go in the space between the pin marked AC and ground, but it's only space that it can move through is in the space in the coplanar waveguide. So you've got copper for what they're calling ground and copper for the power side, and the energy is only in the space between the edges of the foil. So for low frequency, low energy boards, and this is it's an 1.5 amp output, certainly it's not going to prevent it from performing. But if you want to optimize the behavior and reduce losses and improve the efficiency of this design, you would want to keep the copper that you've given away. And what my suggestion would be to have a solid ground plane on layer 2, do the routing on layer 1, and then if it lends itself to that, I would leave the ground on 1. I would do the ground fill on 1, and then use vias to connect that structure together. And one of the results would be these places where you've got components that are connected to this ground bus bar down the middle of the board, is they would be connected with vias to the ground plane on layer 2. So that would help improve the overall behavior, reduce power consumption, improve the layout as far as the fabrication yields. Not that there's any small geometries here, but anything you do to keep the acid fresher means that you get better yields in the behavior of the system. The other thing is that you've got energy coming in on 1, and then it's going to the 2 diodes, one up the board and one down the board. And again, if we had ground on layer 2, they would be working together much better. In this design, the bottom half actually is a little more efficient because the energy is going to be in the space between the body of the diode on layer 1 and the ground stripe on layer 2 for that particular part of the circuit. But all in all, that's the thing I would want to see happen, is to put the ground on 2, bring the traces up to 1, and then wherever you can, leave ground copper, and then stitch that into that 3-dimensional Faraday cage that you want to build, so that you have a lot of copper representing the return or ground. And then that helps make the board even more robust when you look at from an ESD perspective, lowers the radiated emissions, and again, it reduces the energy consumption, so it makes it more efficient. So greener and better all over, just by not throwing away the copper.
Fantastic. Okay, yes. Thanks so much for that, Dan. And aside from that, I see no real fabrication issues. The only other things might be, yeah, like you'd mentioned, the Silkscreen for the polarity and for the reference designators. If we look at the 3D view here, they do have reference designators. We want to avoid putting any references underneath components for assembly and testing purposes in particular, and having the text go in the same direction across the board. There's enough space for it, and I would even make the text bigger because there's just so much space. It's nice that they provided space for the heat sinks. We do see the polarity markers, like you talked about, are missing on here, but overall, it seems pretty good if the copper were there on the top PCB.
I'm absolutely certain this board would function properly. It probably is compliant. Our suggestions are just things in general when you're thinking about a design like this, to help you adjust your philosophy so that you adopt these perspectives, so that you, again, I'm a miser. I don't want to give anything back. I paid for the copper. It's mine. I want to keep it. So find a good way to use your copper, and the results are going to be a more efficient, more robust product that you can give to your customers and expect them to be able to get a much longer product life than you would otherwise. But yeah.
All right. Well, that completes our design review of this board. Did a bang up job with some tweaks you can make and also changing our philosophy and thinking on the fundamentals of PCB design from an electromagnetic fields perspective. Thanks so much for watching this video. We'll see you in the next design review. And like we always say,
It's all about the space.